transformer, etc. What are the benefits of three-phase transformer? That is the reduction in the weight, reduction in the cost, etc. So, and we also discussed delta-delta connection, delta-star connection, star-delta connection, and star-star connection of different connections of the transformer. Then the other two connections are open delta and Scott connection. We'll briefly touch upon that today. But before that, let's work out some more example problems on these four different connections, so that we'll be able to understand it better. Now, coming to this different connections, let's begin by briefly looking at one example problem, and I was in the process of preparing the data for this example problem. So let's call this example problem number 24-1. So we have a three-phase transformer, 33 by 6.6 kV is the voltage rating of the transformer, which are the line voltages. And the transformer is connected in the delta star fashion. That means the primary side, that is the 33 kV side, is connected in the delta, and then the 6.6 kV side is connected in the star. And its rating is 2 MVA. So 2 MVA is the rating of the megavolt ampere, is the rating of the transformer. Has primary resistance R1. So R1 is typically the resistance of the primary. So that is 8 ohms per phase. So that means since it's a three-phase machine, each phase winding will have a resistance of 8 ohms. And the secondary resistance R2 is 0.08 ohm per phase. So I have now both the primary and secondary resistances given. Now the percentage impedance is 7%. So also percentage impedance of the transformer, that is percentage Z, is 7%. Now you can ask the question, is the 7% referred to the primary side or secondary side? And the answer is it doesn't matter, because whether you go to the primary side or in the secondary side, the percentage impedance remains always constant. Now, so it is operating on rated transformer is on full load at rated primary voltage. So the primary voltage, rated voltage, is applied at the primary side. But then the full load, but then the power factor is 0.75 lagging. Now these are all the given data. So what is to find, to determine? That is secondary line voltage. So simply when I say secondary voltage, that automatically means line voltage, because secondary is the star, that is line voltage. Okay, so this data is given to you. So let us use our understanding of one-phase transform, whatever we learned, and try to solve this problem. So first thing you should do anytime when you look at this problem is you try to look at the information that is given and try to use it to the best possible. Now, in order to find the voltage drop, we need to know what is the R and X values. So once only you know R and X values, only then you can find the voltage drop. So let's begin by first calculating the voltage ratio. So for that, let me draw the diagram. So the diagram is like this. The primary side is delta, whereas the secondary side is star. And it is given in the question, that is so just a minute, I think I got a call. Hello. Rating of the machine is 33 kV. So since it is delta, the same 33 line voltage will appear at the phase voltage also. Whereas the phase voltage, the line voltage of the secondary rated is given to be 6.6 kilovolts in the question. So this is 6.6 kilovolts. And therefore this will be 6.6 kV divided by root 3. So therefore the transformation ratio is V2 per phase divided by V1 per phase. The secondary voltage by primary voltage. So this is 6.6 divided by root 3 divided by 33. So let's use calculator and then find out what is this value. (6.6) divided by root 3 again divided by 33. So I am getting 0.1155. So let's use this as our key. So that is the first step in our problem. Next, what we'll do is I want to find out what is the resistance R02. So how to get the resistance? Simply R02 is nothing but R2 plus K square into R1. So what I want to do is I want to refer the entire resistance to the secondary side. So once I refer to the resistance to the secondary side, then I'll be getting whatever is the value of this. So that is equal to, what is R2? 0.08 plus 0.1155 square into 8 ohms is the R1 given to us. So let's try to do that. So I'm getting 0.1867 ohms as my R02 resistance. Now, once I have R02 resistance, but before finding Z02, first I have to find the impedance drop. So how much is the voltage drop per phase? So what you can do is impedance is Z% is 7% given. So therefore, what is the voltage drop? Will be 7% multiplied by the rated current, I2 rated. So this will give me the impedance drop per phase. So this is again phase quantity you have to do. So then this will give me the impedance drop per phase. So for that, first let me calculate what is the, oh, by the way, I think here I made a mistake. See, 7% means whatever is the full load phase voltage, that is 6.6 kV by root 3 the phase voltage, 7% of that will be dropped. Already that is given to us. So what is 7% of 6.6 kV by root 3? So 6.6 into 1000 divided by square root of 3 into 0.07, that is 7% of that. So I'm getting 266.7 volts is the voltage drop. Now then I have to also find the rated current. So how to find the rated current? So this is one part of the calculation. This is another part of the calculation. Now go back and look at the total rating. The total rating of the transformer is 2 MVA. So this is a 2 MVA transformer. So 2 MVA I know, and the voltage rating I know. So I can find out the full load current. So that means root 3 VL IL is equal to the SL. So root 3 line voltage is 6.6 kV multiplied by current IL, that is I2 line, is equal to 2 MVA. So here you should be careful with the units. So the kilo is here and mega is here. So if I calculate kilovolts and megavolts, here the volts will get cancelled. Mega and kilo means here you will get the 2000. So 2000 ampere. So I2 line, that is full load, is 2000 amperes divided by root 3 into 6.6. So let me do that. 2000 divided by root 3 divided by 6.6. So I'm getting 220.8 amperes. I think I made a calculation error. Let me just once again check. 2000 divided by 1.732, that is 2000 by root 3, again divided by 6.6. Yes, so I'm getting 175 amperes. So this is the line current in the full load, but because it is star connection, so I2 full load per phase is also equal to 175 amperes. So now I know the voltage drop and I know the full load current. So I can find out the Z02. So what is Z02? Nothing but I2 full load per phase multiplied by, actually voltage drop per phase divided by I2 full load per phase. So voltage drop I had got earlier is 266.7 divided by 175 amperes. So this will be how much? So I'm getting 1.524 ohms. So like this, I had calculated the Z02 and I also calculated the R02. So from that, I can find what is X02 per phase. So that is square root of Z02 square minus R02. That is square root of 1.524 square minus the R02 we had just calculated, 0.1867 square. So like this. So this is another part of the problem. So from here now I am calculating the X02. Now, so again let me use my calculator. .524 square. So upon calculation actually, so this one will be coming as 1.51 ohms per phase. So now I have everything. So I have the R02, I have the X02, I have the I2, and now I can find out this one. So we already learned approximate voltage drop formula. So I have voltage drop is equal to I2 into R0 to cos phi plus X0 to sin phi. So here we use plus because the power factor is given as lagging. Now what is the rated I2 current? 175. And what is R0 2? We have the value of R0 2, 0.1867. And what is the cost of 0.75? That is cost phi, that is 0.75. Plus, then we have X0 2, that is 1.51 we already calculated. And sin phi, actually if you do sin inverse of 0.75, you will know what is the cost, the phi angle, and then you apply the sin for that, then you can find the sin. So it is coming to 0.66. In fact, you can also do one more way. We can do 1 square minus 0.75 square under root. We will also get the same thing because cos square theta plus sin square theta is 1. So using that also you can find. So anyway, we are just drifting from topic. We are going into something else. So now this all turns out to be some 200 volts. 200 volts is the voltage drop. Now this is per phase. So per phase, my voltage drop is 200 volts. So what is secondary phase voltage? That is rated. So that is 6.6 kV divided by root 3, which is 3810 volts is the secondary voltage rated. So therefore, considering the drop, so what do I get is terminal voltage. Is 3810 minus 200 volts drop, that is 3610 volts, but then this is per phase. Therefore, terminal line voltage of secondary. So this will be root 3 into 3610. So that overall thing comes out to be 6250 or 6.25 kilowatt. So what you observe is, even though the rated voltage is 6.6 kV, under full load condition, the voltage is falling to 6.25 kV. Now, of course, now we can also calculate the percentage regulation. So how to find percentage regulation? Voltage at no load minus voltage at full load divided by voltage at no load. So here I can use 6.6 minus 6.25 divided by 6.6. So let us see how much we get this. So I am getting 0.053, or which is nothing but 5.3% relation. So this is the complete solution to the problem that we had discussed earlier. So I hope you, after solving this, you had understood something. So briefly review this problem. You can pause, like I'll show you the full question once again. So you can look at this, you can pause on this question, and then you can once again try to understand how we had done this problem. So meanwhile, let me proceed to the next problem. So let's call this problem as 24-2, and the problem is somewhat like this. So 100 kVA, 3-phase, 50 hertz, 3300 by 400 volts. Delta star connected transformer. So this is basically the rating of the transformer, what it is and what are its particulars. Then further information given. So the winding resistances. So this is per phase quantity. So what are the winding resistance? So that is the resistance of the HV winding R1 is 3.5 ohms per phase, and that of the LV winding is 0.02 per phase. All right. So under normal full load efficiency, sorry, 95.8% at 0.8 power factor lagging. So the question, what needs to be found out is find the iron losses of the transformer. So again, suddenly if you look at it, it looks very peculiar kind of question. But then slowly if you start formalizing its drawing diagram, trying to understand this question, then it becomes simpler and easier for you. So again, you can pause this video, you can wait for a minute, you can try to see how you would like to solve this problem, and later you can check with my answer. So just I'll give you maybe about half a minute time to think about how you want to approach this problem, how to start solving this problem. Look at the things. So what are the things given for the transformer? So the efficiency is given and full load is given, rating is given. So from all that things I can find out the input. So let us try to do that. First I'll find out what is the output of the transformer. So output of the transformer is nothing but 100, this is under full load. So I am writing full load output 100 kVA multiplied by 0.8. So that will be 80 kilowatts. So 80 kilowatt is the output of the transformer. Now to get the input, it is nothing but output divided by efficiency. That is 80 kilowatts divided by 95.8 or 95.8 by 100, let me put it that way. So again, you should be careful with the units. So finally 80 kilowatt means there is 3 decimal places there. So this one is coming 83.5 kilowatts. So you notice that slightly it is higher. So what are the losses? Losses is nothing but input minus output. So what is the full load output and full load input is what we have to find out now. So input just now I calculated here, that is 83.5 kilowatts minus the output was 95.8 kilowatt, sorry 80 kilowatt. So overall the losses now are coming to 3.5 kilowatt or 3500 watts. So now that you have the output also, so what are these losses? So losses in a transformer is nothing but iron loss plus copper loss. So we are being asked to find what is the iron loss, but then copper loss, it is dependent on the pattern of currents, sometimes more current, more loss and so on that way. But still, based on the given data, we can find out what is going to be the copper loss. So how do you find the copper loss? Because R1, R2 is given, we can calculate the equivalent impedance of the transformer, that is equivalent resistance of the transformer, refer to secondary side. Another thing is, because the ratings are given, I can also find out what is the ratings of the current, and then from that I can find the solution. So let me write down that part now. What is the copper loss and what is the iron loss? So iron loss is ultimately what is asked. So copper loss is nothing but so here I am getting 3500 as the total loss. Just a minute. Yeah. So first I have to find out what is my, in order to find the copper loss, what is my rated current. So how to find the rated current? That is, just find what is I2. The rated current I2 is nothing, is that, so this is again line current, is nothing but the rating of the machine divided by root 3. The machine is 100 kVA. So 100 kVA divided by square root of 3 multiplied by the line voltage of the secondary. So that is also given in the question, that is 400. So now if I do this calculation, that is 100 kVA divided by root 3, 400 kV. Let me confirm, is that 400 kV? No, it is just 400. Okay, so this, if you do this calculation, you'll get 144 amperes. So I had known the current, but still to find the copper losses, I need R02. So R02 is nothing but R2 plus J case, sorry, not J, K square into R1. So what is R2? R2 given in the question. So R2 given in the question is 0.037 plus K square. So what is K? K we haven't found out, right? R1. So what is R1? .5 ohms. So in order to solve this, we need to know what is K. So K is V2 per phase divided by V1 per phase. So V2 is 400 volts, but then the transformer for a 400 volts V2. So where do I get this 400? This 400 I got from the question itself, that the rating is here, and it is delta star connected. So because the secondary is star connected, so actually the phase voltage will be 400 by square root of 3 and divided by V1 phase, that is 33,000. How much is that? 3.3 kV. So with this, I can find out what is K. 4 by root 3 into 33. Now I can substitute this K here. So therefore, R02 equal to 0.037 plus K square. 4 by root 3 into 33 square into R1. So what is R1? .5. See, all these values are given in the question itself. So now if you simplify this calculation, you will get finally R02. That is, apparently it is 0.037. So I run out of place. So R02 is equal to 0.037. So now I have everything to calculate the resistance. So I think this is 0.02 here, not like this. So now I have everything to calculate the copper loss. So let me go to a new page. So now total copper loss equal to nothing but 3 times R02 I2 full load square. Since secondary side is anyway star connected, so I can do that. 0.037 multiplied by how much was our I2 that we calculated? That was 144.1. So again, if you simplify this, you will get 2305. Now we got 2305 watts. So this total 2305 watts, I add to the iron loss. Like I know the total loss. So this is total copper loss, WCU. So W total is 3500 from the efficiency we calculated that. So therefore, W iron will be 3500 minus 2305. So how much is this? 1195 watts is your. So this is the final answer for again our problem. So again, given this problem, I think I'll have to share the screen. Yeah. So I'm just going back to the first. Given a problem. So if you have any doubts, feel free to ask. I see some students joining the class. So if you have any doubts, example 24-3. So what we want in this is something like this. So given data, 11,000 by 6,600 volt, 3-phase star delta transformer. So this is the rating of the transformer. I mean, this is the details of the transformer. Rating is not given. Now, this transformer, the secondary load is a 6.6 kilovolt 3-phase motor with star connected stator. Developing 970 kilowatts at kilowatts of output power at .9 power factor lag and efficiency of 92%. So this is the entire set of given data. Now given this data, what we have to find out? So let me write to find. So first thing we have to find is motor line current, line and phase current. Second thing we have to find transformer secondary. Phase and line current, secondary current. And third one you need to find is transformer primary current. So this data is given to you. What is the motor line and phase current? What is the transformer secondary phase and line current? Transformer primary current, everything. So again, take a minute, look at the data, what data you have, and try to understand the data, try to draw a diagram, and then try to solve it. Meanwhile, you just take a minute understanding this problem, and I will solve it once you have understood the problem. Just take a minute, look at the problem. Now try to solve this problem. So as usual, it helps if you begin by drawing a circuit diagram for this. So what is given is first star delta transformer. So first I have a transformer. It's a three-phase. So I draw the circuit diagram like this. Three-phase supply, and then I have a star connection for the windings. Then I have a delta transformer like this. Then, so this is the core, this is the primary, and this is the, so instead of primary, secondary, I'll write the ratings. So what are the ratings? 11,000 by 6600 volts. So, or 11 kV by 6.6 kV is the voltage transformation. So again, this is line voltage and this is line voltage. That means the voltage here will be 11 kV and the voltage here will be 6.6 kV. Not only these two lines, now what is connected as a load here? What is connected here is another motor. So there is a motor, and the motor is stator winding is connected in star, and the motor is connected as a load. So the motor converts electrical energy into mechanical energy. So the output of this motor, so the motor output that is given in the question, how much is the output? 970 kilowatt. So, and the efficiency is 92%. That means if I know the output and if I know the efficiency, so I can find what is the input to the motor. So what is the input to the motor? So first let us do that. So input to the motor, output by efficiency. So 970 kilowatts divided by 0.92. So that is 970 divided by 0.92. 1054 kilowatts. So almost 1 megawatt we are getting here. So this is 1054 kilowatt going to the machine. Also the power factor of the machine is given 0.9 lag. So I have the, so then from all these I can find out what is the line current here. So how to find the line current of the motor? How to find line current of the motor? So we know that √3 VL IL cos phi is equal to P, power. So the power that is output we already know is 1054 kilowatt, right? 1054 kilowatt, and the power factor is 0.9 here, √3 is a constant, and the line voltage should be maintained 6.6 kilovolt. So IL itself is unknown. So this implies that IL will be what? So 0.94 divided by all this cancel. So here kilovolts and kilowatts will cancel. You you can find amperes to be the unit there. So 1054 divided by 0.9 divided by 6.6. So again divided by 1.732. That is the square root of 3. So finally I am getting 102.5 amperes. So what is this current? Basically 102.5 amperes. This is the line current of the motor. So let me once again check the calculations. $970 kilowatts. $1054. Okay, that is correct. And okay, so this is the line current of the motor. And once we have the line current of the motor, what else can we find? Now this is phase current of the motor also. Because motor is star connected. Line and phase currents of motor. So once I have this, next look at the diagram. So 102.5. So here the currents that are going 102.5 amperes, 102.5 amperes. Of course, this is only the magnitude. The angle will be different, 120 degrees apart. Excuse me. So now what will be the current here in the winding of this transformer? So because this is delta, so the current will be 1 by root 3 times here. So 102.5 divided by root 3 is what we have to do. In fact, current in secondary of transformer, so let's call it line current, is also equal to 102.5 amperes. So now phase current in secondary will be 102.5 divided by square root of 3. So I'm getting 59.17 amperes. So this is the current that will be flowing in the transformer, secondary. Now the question is, what is the primary current? Now here, what about the losses of the transformer? So because the data is not given in the question pertaining to losses of the transformer, so how much is the losses in the transformer not given? So therefore we can assume that the losses to be assuming there are no losses in the transformer, so this input power will also be 1054 kilowatt. So strictly speaking, if the losses of transformer are given, we have to add them, but let's not worry about the accuracy here. So now, because that data is not given, from this I can also find the line current in the primary. So what is the line current in the primary? So we have root 3 VL IL cos phi is equal to power. Now root 3 is same. VL is now 11 kV or 11,000 volts. And then IL. So IL is unknown right now. And the power factor of the primary may be different from power factor secondary. But then again, let's assume that there's no reactance drop in the transformer. So I can still use the power factor as what was that, 0.9 is equal to 1054. So from all this now, this is kilowatts. From all this now, I can find out the IL. This is in the primary. So 3 zeros and kilo will cancel out here. Volts and watts will bring out amperes. And then I have 1054 divided by 0.9 divided by 1.732. So I'm getting 676.16 amperes. So hopefully, if everything is correct, there are no mistakes in this, we can actually move forward. So any doubts in this question, feel free to ask. We have about 10 minutes left. So meanwhile, I want to cover 2 other topics. So just I'm giving you a minute time. If you have any transformers, you can still make the 3-phase system work. So that is the interesting thing about it. So let me show that diagrammatically. So let's say you have 3 transformers. This is first transformer. This is second transformer. And this is third transformer. So what is the delta-delta connection? Delta-delta connection. So the ending of the first, you connect to the starting of the next. The ending here you connect to the starting. The ending here you connect to the starting. Similarly, ending connect to the starting. Ending connect to the starting. And then ending you connect to the starting. And then you take out the terminals. So this, let's call this as terminal A. And let's call this as terminal B. And let's call this as terminal C. So like this. And then here on the secondary also, let's call this small a, small b, and small c. Corresponding terminals on the secondary side. Now imagine one of the transformers is damaged. So, let's say this transformer is damaged. So now if you damage, then you have to disconnect this transformer. So how the transformer is disconnected is that first this wire is removed here. So if I remove this wire, so I get something like this. So, and this wire also you can remove. Similarly, this wire you can remove, and this wire you can remove from here. So now eventually what you get is a different diagram. Okay. So what you get is, this is equivalent to open delta. So what is the open delta connection? It is like this. I just have 2 transformers. So here the terminals are like this. This is capital A, capital B, and capital C. And this is small a, small b, and small c. So you notice that this is exactly same as the earlier diagram. Only thing is for this, the power consumption rating will be, so in open delta connection, the power rating will be reduced by a factor of 1 by square root of 3 or 57%. So this way it will be reducing. Now this still works. See why it still works is, let's draw the vector diagram. So vector diagram. So you know that this is VAB, VBC and VCA. So this is the three-phase supply applied to the primary. So this now these are the line voltages. Now the corresponding to VAB, see what is the secondary induced EMF? See this is VAB, capital A, capital B, and this is VBC. Then correspondingly small AB will come here and small bc will come here. So what will be the output? Output will be small ab will come here and small bc will come here. Now what happens if I simply see why these two voltages are coming? Because they are induced in the two transformers. Now the third voltage will automatically appear without even anything. See why it should appear is, if I simply measure, so this is plus minus, this is plus minus. If I take a voltmeter and measure the voltage, so I measure the voltage like this. So I'm interested in voltage of C with reference to A. So what is voltage of C with reference to A? It is nothing but, you see, this is, if I want to know voltage of C with reference to A, I start at A. So this is minus VAB, because from plus to minus I'm falling. Then again minus VBC. So the addition of these two will give me what is VCA. So which in turn comes out to be the third. Sorry. So this is VCA. So this is the output voltages. So even though one of the leg is not there, still the transformer can work based on only two phases or two windings. But only the thing is the capacity reduced by 57%. Now one final topic I want to cover, because we are running close to the closing time. So the topic that I want to now write about is Scott connection. So in Scott connection, what you do is you take two transformers like this, and we take a center tap here and here, and then connect these wires like this. Now, once the sensor, this is there, now you have, this is the primary A, B, and C, and this is the secondary side, A, this one, B, and C. So this is a kind of, again, a peculiar connection, and this one is again credited to be invented by one Mr. Scott. So that's why on his name this particular connection is there. Now, how do you analyze this? See, look at the voltage. So what is the voltage here? So it is VAB. I'm sorry, capital A, capital B, because it is between the terminals A and B. And what is the voltage here? You have, this is VBC, B and C. Sorry, this is, here we'll have half of VBC and another half of VBC. So here you have plus minus, again plus minus like this. Now, if I am interested in knowing the voltage between this point, and this point, because what is happening now is that so this point is connected here. Yeah. So the entire VA, in fact, actually the VAB is not from here to here. So let's call this point as D. So this is VAD. So VAB is completely here. So if I take this total voltage is VAB. So from that, if I subtract half of VBC, then I'll get the voltage VAD. That voltage is coming out here to the output side. So see, we have VAB and then we have VBC and then I have VCA. So half of VBC is somewhere like this. So that half of VBC we have to subtract from VAB, then you will get a voltage, somewhat voltage like this. So in other words, the standard textbook diagram, if you see for this, is the Scott connection. It is like this. So eventually it is exactly like this. So I am not drawing, since the time is less, I am not drawing the full this one. You just refer to, this is the basic idea. This is the basic connection of Scott connection. And the purpose of this is that we can generate a two-phase voltage from a three-phase voltage, or you can generate a three-phase voltage from a two-phase voltage. So that is the advantage of this particular Scott connection that we have. So I know I have not covered this in full detail, but then just you can refer to any standard textbook. They will also explain further. I have just given you the basic idea of these two connections, that is Scott connection and then open delta connection. So any doubts up to here?